Hello, Internet. Today we're going to be looking into one of the classical concurrent programming problems. It's called the Dining Philosophers, or at least that's how I was taught. So this problem is, think of a bunch of people sitting around a table. They each have a bowl of noodles or ramen or something that they need to eat, and they need two chopsticks in order to eat that, because if you've ever tried to eat noodles, actually it kind of works all right. Let's say it's rice in the bowl. You can't really do rice with one chopstick. So there's rice in a bowl, and there's a chopstick on either side. The issue is they're all sitting in a circular table, and there's only one chopstick on either side. So the philosopher is going to share a chopstick, the right chopstick with the person sitting to his right, and the left chopstick with the person sitting to their left. And they can only eat if they have both chopsticks. And so the reason this is important in concurrent programming is because if you just do this without any sort of synchronization or any sort of control in your program, what's going to happen is somebody may grab the left chopstick, for example, and not be able to get the right one. And when that happens, then they're just stuck. And that left one is still there. So what do? They just hold that, and then suddenly nobody can get that. So the person to his left can't do anything, but he may grab the left, and then it just goes all the way around the table, and everybody just stops. And eventually nothing gets done. And that's called deadlock. It's when a program kind of works itself into a state where nothing is actually happening. And then there's also an alternative to that called like live lock, where you kind of have two tasks that keep switching each other on and off, sort of like turning a light switch on and off. Have you ever seen those boxes that kind of turn themselves off after you turn them on? Imagine if something was configured to turn it on again, and it would just keep doing that. Anyway, what we're going to be doing is we're going to be solving the Dining Philosophers with Async and Await in C#. And we're going to be starting with nothing. So this video may run a bit long. I'll try to cut out the boring bits, but we're going to try to just write a really simple console application to solve this problem. So what we need is a number of philosophers. So I'm just going to code this in as an int. We can fix this later. We probably won't. But you can attach this to, say, one of these arguments if you want. We're not going to do that. So int, we'll just call it philosopher. I should have chosen an easier name because that is not how you spell philosopher. We'll start with 5. Nice odd number. Are you going to be smart? No, does it not have? Oh no. Okay, I guess we're keeping my terrible spelling. That's not how you spell philosopher. It's not even close. All right, so we've got a philosopher number, and we're also going to need a list of tasks. So we're going to have a task array that's going to be our philosophers. I didn't spell that the same way I spelled the last one. All right, anyway, we've got our philosophers, and we're going to have, let's call it just a Boolean array of our chopsticks. And so we can use a Boolean array here because all we want to know is if they're being used or not. So what's going to happen is when somebody wants to eat, they'll have to acquire both of the chopsticks, which means they're going to have to set them from, say, true to false. And then once that's been done, then they can do their thing, maybe wait a bit, and then return them back into the queue. So at the end, they'll just undo themselves. And then a task is C#'s threading tool. So a task and a thread, when you're working with concurrent programming, or if you're familiar with like Java, threads are different than tasks. A task is a lot more action-based. It's based upon something you do. So a task is something you do on a thread. And so a thread is something that's running in parallel. So you can have two things happening simultaneously on your computer. They don't necessarily have to happen exactly simultaneously, but the idea is that how they run is indeterminate. So one may go and then another may jump in and another one and so forth. So that's a task kind of does that, but it takes it and kind of abstracts that away and kind of runs on top of threads and says, these are things that I want to do asynchronously. So we're going to keep a list of those, and they're just going to be what our philosophers are doing. Specifically, they're going to be them eating. That is not spelled right. Anyway, what we're going to do is for the number of philosophers, we're actually going to initialize things. Philosophers equals a new task array of the philosopher number. Did I not do that right? What? Okay, copy, paste. What is going, oh, static, duh. What am I doing? Okay. It's late and it's been a long day. Yeah. Anyway, we're gonna carry on because that's what we do in these. We get things done. Or I talk a lot and don't get anything done. That's also an option. We can do that too. Let's see, we need to initialize our chopsticks too. And that's gonna be a new Boolean array. Same initialization, like that. So there's nothing in here yet. We haven't set it to anything, but that's fine. We just need to allocate that memory. So now, we'll just actually initialize things now. So I'm gonna loop over this. I is less than the philosopher number, and we'll just increment that. So this is gonna be a basic loop, and then we want to philosophers I equals generate new philosopher. And we'll pass in the index of the philosopher so we know where they're sitting on the table. And then we also need to initialize the chopstick at the same position to be, do we want it to say it's in use or not in use? False. So what this is going to say is if the chopstick is not being used, it's going to have a false value. So I'll actually comment that here. Not in use. Okay, just so we remember, because I will forget. We could do this better. Let's create an enum called chopstick state. Sure. And what we're going to do is to have, I don't know what we want to call this, eating and not in use. I feel like that's wrong. There we go. Gave it the wrong name there. Okay, so everything is as it should be now. And then we can change this Boolean to be a chopstick state. Change that to be a chopstick state. And change this to be chopstick state dot not in use. And this way we just get a more concrete thing. So we're not kind of trying to figure out what the Boolean actually means. We have something that says it's not in use. So that just makes everybody's life way easier. So this function doesn't exist. So what this is going to do is we are going to want some sort of iteration number. So this is going to be the number of times they're going to eat in a loop. So for I is going to be less than however many times we want them to eat. 20? Sure. And so how this is going to work is if chopsticks, let's say is well, how do we want to do this? Let's do get chopstick. And the reason I'm doing a getter here is because we're going to need a modulus here. And I'll get to that in a second, but for now, let's get this out there. So if this is equal to not in use, chopstick state not in use, and our get chopstick I plus 1 is equal to not in use as well, then we want to get both of them again and set it equal to, oh, this isn't going to work. Shoot. So we actually need to be able to set this back. So we actually need the index. So this won't work because that you can't set that. Anyway, so this was a good idea. Get chopstick index. Okay, this is starting to look less nice. We can fix it later though. So a lot of the times, and if you've watched my videos, you know this already, but I write really gross code initially, and then I say, we'll fix this later. And I say that a lot, and it's not just in these videos, I do that all the time. So part of the reason for that is because right now we're just kind of getting an idea on the board. And then once we get it there, we can kind of see how everything works and fits together. And then we can kind of split it off into its parts. So before, it doesn't make sense to make something look good before you've actually solved the problem. So let's solve the problem and then we'll make it look good. Anyway, now we're getting a chopstick index at both of those positions, and then we're doing some fun stuff there. Sorry, my cold is still there, apparently. So we want this to be equal to eating. And let's do it for the +1 as well. So now we've set both of those to be eating. And at the end of this, we're going to want to set these back to not in use. Like that. And so in here is our do work section. So we're going to do console write line, something smart. Philo. Shoot, I forget how this syntax works. And I'm gonna feel silly. Oh, it's out in front. Hold on, one sec. Minor technical difficulties. I am guessing in the dark. Philo of, so this isn't gonna work. This isn't gonna work at all. Okay, sorry. Noticing problems all over. Philosopher index is what this has to be. And the reason for that is because we used I multiple times, and that won't work at all. So we need to change all of those to be this. This is just a loop. There shouldn't be anything specific to our actual tasks here. It's just a loop. So now we're doing this. This is a clever C#6 way of, I think it's C#6, way of getting a variable. So we're taking our variable, plugging it into the string. It's sort of a shorthand for formatted strings. So you just precede your string with a $, and then you just surround your actual variable in brackets, and it will just do it for you, which is way nicer than doing like what you had to do before with the string formatter or concatenating a bunch of strings. This works better. So use this, or don't. It's up to you. I don't care. I don't have to read your code. So now we're going to actually capitalize things. I've been working in Java too much, and that is still spelled wrong, but that's fine. So we have this console write line, and so fill of whatever the philosopher's index is going to eating. Sure, I was going to retype something smart, but then I didn't. And then we are going to delay. Yeah. So we're going to do a delay here for 100. I don't need 100 milliseconds. That's not how that works. So we'll just delay for 100, which is going to be 1/10 of a second. And so now we've got a short delay. This just kind of makes sure there's a context switch in between there so that we can actually see what's happening. So there's a bunch of ways that threading can happen. Like we have a console, and that's just there. It's on the one thread. It's on the UI. And so a lot of things need to access that. And in order to actually get everything to kind of talk together, there's context switches that happen. And these are, in threading, they're fairly slow. So the best idea is to minimize those if you can. So we're trying to do that, or well, actually we're trying to force that to happen. But anyway, the idea is to minimize that when you're writing good code, because then you don't have to worry about, well, context switches, which is going to swap out all of the memory for that thread and put it somewhere else and bring in the new thread's memory. And so the processor is just going to keep cycling those out. And so every time that happens, it has to take and offload all that memory. And that takes time. And that's time you aren't doing what you need to do. So we're doing this, and this way we'll actually get multiple things happening interjoined instead of it just running through this entire thing in one without doing any switching or anything, which would be boring. So now we've got this. And one more thing, I'm going to put another message up here and just say, attempting to get food. And so they're going to do this and wait until they can. We'll actually stick this in a while loop. Actually, isn't there a do until? No, that's not a thing. What did I do? I broke everything. So what I'm noticing is this may just loop through. Ideally we want a wait. So if this doesn't happen, if this if doesn't evaluate to true, so if they can't eat, we want them to kind of block and wait for that. So trying to think the best way to do this. I know the wrong way to do it, but I don't know the right way to do it. Actually, let's just do it the wrong way, and then we could do the right way in the next video, and we can see if anybody thinks of any clever solutions to it. So we're actually going to take out this chopstick state, and we're going to actually use a semaphore slim. And so what a semaphore is think of it as a counter. So a semaphore is going to have some sort of number in it. And what it's going to do is when you try to get in, when you call one function in that, it's going to decrement that counter and see if you're below a value. If you get below that value, it's going to block you until it gets above whatever that value is. And then the alternative one is obviously releasing it back and saying we're done with this. And so that actually works really well for our chopsticks. So what we can do is actually plug that in and just have each chopstick be a semaphore. So this doesn't actually work, and we'll get to that in a second, but it will kind of work, but it won't work. So what this will do is instead of all of this fun stuff, we can just take our chopstick and acquire it, like so. Wait. So we just want to wait for it. And the next one is also just going to wait for it. So we have the two chopsticks we want. We're just going to wait for both of them, and that's going to be good. And so what's going to happen is so it's our turn to eat, we go and grab one, and then we grab the other, and then we start eating, and that should be good. So now we do this, and hopefully we can do a release here, and that will just release them back. So now somebody else can use them. Now there's one problem with this, and it's pretty much, this doesn't actually work. And we'll get to that right now. So the reason this isn't a valid solution to this is what happens if you can only grab this one? What happens if you can only grab this chopstick, but somebody else has this one already? If that happens, you're stuck. But not only are you stuck, but you've already taken this and you aren't going to release it until you've already had your stuff. So it's like if there's like a fork and a spoon, it's like grabbing the fork and then somebody else at the table grabs the spoon, and then you need both to eat. So now what? You just kind of glare at each other really evilly and hope somebody gives in, but nobody can because there's no way to do that. So we'll need to fix that. And that's what we'll be doing in the next video. But for this one, I'm going to show what happens when you get a deadlock. I think that makes sense. And that way we can actually keep this video reasonably long because it's already like 20 minutes in and we haven't even gotten to solving the fun problem. So let's do this and then we can do that next. Those were words. All right. So we have an int of our index, and this is just going to return our index mod. That's not mod our philosopher number. Sure. So what this is going to do is say you get 5. It's going to take the modulus of that, so it's going to get the remainder. And in this case, it's going to return 0. So then we get 0, and so what's actually going to happen is say you are philosopher number 5, which means you're actually philosopher number 4 due to starting at 0. So if you're there, you're actually going to have chopstick 4 and chopstick 0. And so that way, this just makes it really easy to get that. And it prevents us from having to embed this in here, which would actually be shorter, but I don't like doing that. So anyway, here's what we have. We have really quick modulus. We have the acquiring of semaphores and a bunch of other stuff. So actually, we don't even need this if. Why do we don't need that? All we need to do is just acquire both of them and then do our work and then release them. Super simple. So we're just going to do a task.run on this. And so all this is going to do is create a task and run it, which is about as simple as you can get, really. And I am totally messing everything up. So all task.run is going to do is it's going to create a task for whatever lambda expression or delegate you give it. And so in this case, all we're doing is saying loop 20 times and eat. So that's all it's doing. And then we're returning that like so. Okay. Now we already are setting it. So all we need to do now is do a task, wait all on our philosophers. And so what this is going to do is just so we don't like end our program immediately, because all of this stuff is happening asynchronously. So our main thread is going to think, oh, cool, we're done, and just kill itself. We don't want that to happen. So what this is going to do is this is going to say, given a list of tasks, don't go past this part until all of these tasks have finished. And so this is going to wait until everything is done. So we're just going to wait until all of our philosophers have eaten, and then we're going to do a quick write line of finished eating. Huzzah! There we go. Cool. So our program should work, and hopefully it compiles. And my voice is going all funky. So if we start, whoa, did it actually work? It wasn't supposed to actually work. Hold on. So I'm going to stick a read line at the end just so we can see what happens. There we go. So now we have deadlock. So this didn't actually hit our read line. So I can hit enter all I want, we're not going to get past this. And you can see Philosopher 3 is attempting to get food, but they can't get anything. And that's probably because they acquired the first semaphore and didn't do the other one. And the first time it completed, we just didn't have that case. And so this is what makes threading really annoying. Like you see this one, it worked fine. Everybody finished. But that's a problem because, well, everybody finished. It looks like it worked fine. So if you just run this solution once or twice, you may be like, oh yeah, this works, and just ship it. Why not? But it's a little bit more complicated than that. And that's what these race conditions are all about. And so finding out what they are, I can't even get it to happen again. I'm actually kind of surprised. I would assume it would happen quite a bit more than this. We can make this happen. There we go. Just increase the number of times they have to do something. There we go. So now we're locked with Philosopher 1 attempting to get food. So this is a simple way to not write concurrent programs. So we'll be fixing this in the next video, which I should have up probably the same day because I'm recording this at like midnight. So this isn't going to get up today. But anyway, we are going to figure this out tomorrow and get it up and working. And then you can see how to solve this problem. There's actually a number of solutions to this problem. So hope you guys enjoyed it. And if you did, let me know what you liked in the comments, and hopefully leave a like because I like those. I think that makes sense, right? Anyway, I hope you guys enjoyed it, and I'll see you guys in the next one. So see you, Internet.